All right. So hello, everyone. Welcome to our computer science department seminar. So in this week, we have Dr. Akshay Krishnamurthy from Microsoft Research at New York City to visit us and give a talk. So let me give an introduction. So Dr. Krishnamurthy is a principal researcher at Microsoft Research, New York City. Previously, he spent 2 years as a assistant professor in the College of Information and Computer Science at UMass Amherst, and a year as a postdoc researcher at Microsoft Research, New York City. He completed his PhD in computer science department at CMU, advised by Professor R.T. Singh. Akshay's research interests are broadly in machine learning and statistics, more specifically in interactive learning or learning settings that involve feedback-driven data collection. So recently, his work has been focused on decision-making problems with limited feedback, such as contextual bandits and reinforcement learning. So please join me in welcoming Dr. Krishnamurthy to give a talk in our seminar.
Hi, thanks, Chuan. It's really great to be here. I kind of wish I could have come in person because I'm actually from California, and it would have been great to go back to my home state. But anyway, here we are. So yeah, let's jump into it. This talk is going to be about representation learning and exploration in RL. And this is something I've been kind of obsessed with for several years now, and some pretty recent work that I'm quite excited about. Okay, so when I started thinking about reinforcement learning, we started thinking about these problems where you have a very high dimensional state space, or your agent is going to perceive raw inputs from a camera, and is going to try to use this high dimensional sensory information to make decisions about what to do and optimize for long-term outcomes. And we see these problems in gaming all the time. When we train agents to play Minecraft, they operate on the raw pixels that are coming from the game, and they have to walk through these long mazes and stuff like this. And we're actually getting kind of good at this because we have Minecraft is a simulator. We can run these agents in parallel in training, and we can collect tons of experience. And so we're doing quite well in gaming. And of course, I'm sure a lot of you have seen some of the successes in Go and StarCraft and stuff like that. But once we move beyond the simulated setting to problems in robotics or maybe in dialogue, we actually haven't seen a lot of success in deploying reinforcement learning in these problems. And in part, this is because in robotics and dialogue, you just don't have that much data, and you don't have a good simulator. So it's just much, much harder to train these agents for billions and billions of episodes, or for collect tons and tons of data with these agents. And so when I started thinking about these problems, I wanted to really focus on sample efficiency. And so when I'm a theoretician, so I'm starting to ask myself, how do I build provably sample efficient algorithms for sequential decision making in the problems where these very complicated problems where you have a high dimensional input? So I want to take some time just to make sure we're all on the same page about why this problem is hard. And these kinds of problems require an algorithm or an RL agent to do 3 things. And these are exploration, credit assignment, and generalization. So exploration is the agent has to make decisions in the environment to collect the data that it needs. It has to plan to collect the right data. And that's something that a lot of popular RL algorithms are not very good at. The other one is credit assignment, which is that the agent has to be able to attribute, when it observes an outcome, it has to be able to make a decision about which action it took in a long sequence of actions that caused the good or bad outcome. So John Langford likes to say, which move lost the game of chess? You play chess, there's 100 moves, you lose at the end, and you have to understand why you lost. And that's what credit assignment is about. And the third one is generalization, which supervised learning is just amazing at, right? We have to be able to use experience we've collected in the past to make decisions about things we've never seen before. And this, supervised learning is just really phenomenal at this. And so, these are the 3 sort of core capabilities that we'd like our RL agents to have. And the first way to think about this problem is we can ask, can we do 2 of these things at the same time? And the answer is actually, yeah, we can do any 2 of 3 at the same time. So, on the top left is this tabular reinforcement learning. These are problems where the state and action spaces are very small. And here you do have to explore, because you have to plan to visit states you've not seen before, so you can collect new information. You also have to do credit assignment because you have a long horizon. And so, and we're very good at this, and we understand these problems. Basically, we have a complete theory here. On the top right is policy search methods like policy gradient, which can do credit assignment and can do generalization. These things are amazing because you can parameterize your policy using a deep neural network, and that will take care of the generalization. And this policy gradient theorem is basically taking care of credit assignment for you. And on the bottom is contextual bandits, which is reinforcement learning with a very, very short horizon of just one. So you see a state, you take a decision, and you see a reward, and you're just trying to optimize for the short-term reward. And here you still have to explore because you have to explore over the action space, and you have to generalize because the states will be different all the time. But we're actually quite good at this. This is a much, we don't have to do long-term planning, so we don't have to do credit assignment. And so these problems are quite a bit easier, and we are actually able to solve these problems in the real world. Like my group runs a contextual bandit product that we deploy with customers and make money off of it. So these are like, the first way you might start to tackle, like, how do we build algorithms that have all three of these capabilities? To say, how do we get 2 of 3? And we've basically done that. And so now we're ready to start thinking about how do we get all 3? And this is sort of what this talk is going to be about. And let me just try to drive this point home with like what I think is of a crazy difficult reinforcement learning problem. So the agent is going to start randomly in 2 states, S1A and S1B. From each of these, there's going to be one good action. Let me see if the laser pointer is working. So there's the good action, which will transit you uniformly to the good states at the next time. And there's going to be 10 or 9 bad actions that will transit you to the bad state. And from this bad state, you will not be able to get any reward. And from the good states, there'll be some more stuff you can do. And you repeat this process 100 times. And if you've taken a good action all 100 time steps, at the very end, you'll get a high reward. But what I'm going to do is I'm going to create an anti-shaping. So I'm going to give you a small reward if you go to the bad state, like at any time. And so until the agent has discovered that there exists a high reward at the very end, it's going to be incentivized to actually fall down right at the beginning, right? And so this is like kind of a very hard problem because, well, you have stochastic dynamics, you have an extremely long horizon of 100, you have this anti-shaped reward that's encouraging you to do the wrong thing. But as I've written it so far, this is just a tabular problem because there's like 299 states, there's only 10 actions per state. We have algorithm. This is like, we actually don't have to do generalization. So there's no, only 2 of the 3 capabilities are required here. So what I'm going to do is I'm now going to make this problem much harder by, instead of showing the agent the state, I'm going to show it a high dimensional observation that is generated from some distribution associated with each state. And so now when the agent interacts with this environment, it will never see the same observation twice. And it really will have to generalize in order to solve this problem. So this is like some extremely hard problem that we cooked up just to like sort of see what state-of-the-art algorithms do. And you run PPO on this problem and it just completely fails. It just falls over immediately. So this is what I'm showing you here is the coverage of PPO. So this is like time step 1 and this is time step 100 over here. And I'm just showing you the frequency of time, the amount of time PPO spends in each state. And you can see it just like never gets to the good state at the end. I mean, it doesn't even get to the good state at like time step 6, right? So you run PPO and it just like falls on its face. And so what we'd like to do is, build some algorithms that can solve these kinds of hard problems. So when you think about, when you think about this problem a bit more, you can, maybe a solution strategy kind of emerges, which is, so these observations are generated from the latent state, but sort of under the hood, you have a tabular Markov decision process. You have just 300 states and just 10 actions, and all you need to do is sort of do dimensionality reduction, where you take this observation and you say, oh, this observation actually means this discrete state. And so what this is like representation learning. So this is the kind of thing that it seems like a plausible solution here, where I'm going to take a neural network and I'm going to try to learn a neural network that maps my high dimensional observation into the state space and then run a tabular algorithm on the states. So this is the kind of idea. We're going to try to decode the latent state from the observations and then apply a simpler or a tabular method on the latent states. And that's like the approach we're taking here. And I kind of like this approach if you think about it conceptually, because the idea is we're sort of decoupling the way the system evolves with the dynamics of the system from the way the observations are generated. So this allows the dynamics to be relatively simple, which seems to be like part of the difficulty in reinforcement learning, while the observations are allowing us to model like real life scenarios. And that's, when the observations are arbitrarily complicated, this really forces us to use nonlinear function approximation, yet the dynamics are simple enough that these problems remain tractable. So that's like the conceptual approach that we're taking over here. And okay, of course, the challenge is that the representation learning part, where we're trying to decode the state, and the exploration part are highly coupled, because you cannot, it could be like, maybe you cannot explore unless you have a good representation, but you cannot learn the representation unless you've explored the system, because you need to collect the data from the states to learn how to decode them. And so the whole challenge is that these two things are kind of intertwined, and we have to sort of unlock this this chicken and egg problem. So that's kind of like what I'm going to talk about today. I'm going to tell you like two different dynamics models, latent dynamics models, and two different algorithms for this. So maybe now is a good time to pause if there are any questions. Otherwise, we'll just dive into the first part. I can also see the chat, so if you want to just chat a question. Okay, cool. So the first part is about this notion called kinematic state abstraction, and this algorithm called Homer. And this is Homer Simpson over here. And this is joint work with Dipendra Misra and Michael Hanoff and John Langford. So going off this theme of a latent state model, let me just define like a precise model that we might work with. So this is going to be like a rich observation problem. So the observation space is going to be arbitrarily complicated. The latent space is going to be discrete and finite. Okay, so the way it works is, the agent at any time is in some state. You can think about it like the position of the agent in a grid world. The agent is not going to see this information. The agent is instead going to see some image or some observation, which is like, imagine the agent has a first-person camera mounted on its head, and it just sees the pixels from the image. And then it takes an action, it transits to a new state, and sees a new image, and so on and so forth, right? So this is sort of like how the dynamics are governed. There's a discrete tabular state space, a small action space, and a very, very high dimensional observation space. I'm reading this question, very basic question from a networks person, but insofar as working in these environments is quite difficult, how do biological agents perform so well in the real world with such limited samples? Yeah, I don't have a good answer to that question. I've heard a lot of theories, like sometimes, we have a lot of information genetically encoded. We're very good at unsupervised learning. I don't have a great answer. I think in some sense, we have very good inductive biases. Like maybe this is my take as a learning theorist, but we have very good priors. We're very good at generalizing in between tasks. These are not going to be questions I'm able to address at this stage. Like I'm thinking about maybe far, far simpler problems than what like biological agents can do. What were the three criteria? Generalization, credit assignment, and exploration. Okay, great. These are great questions. Okay, and so because the observation spaces like images are very high dimensional, you really have to do nonlinear function approximation. When you're dealing with images, you basically have to use convolutional neural networks. So that's important. And just because, if you think about this problem for a little bit, you will realize that this is actually like a POMDP. And I don't want you to think of it that way. So what I'm going to assume is that the latent states, the S's, are decodable from the X's. And I'll tell you what a formal assumption is. But don't think about this like a partially observable problem. So the formal setup is I'm going to think about an episodic reinforcement learning setting. So the starting state is drawn from some initial distribution. The S's are always latent. You'll never see them. And then you are going to proceed for H time steps where you observe an observation, an X, from an emission distribution associated with the state. You're going to take an action. Then the latent state is going to transition according to a transition operator T. And then then you repeat. So then you see SH plus 1, and then you go back to here. Okay, and what I'm going to assume is that the state space and the action space are finite and relatively small. The observation space is infinite and arbitrarily large. This decodability assumption that's going to avoid partial observability is that there's this Q distribution, which is the emission function. And this Q distribution, the support for each S are going to be disjoint, which means that each observation can only appear from one state. And therefore, this is actually a MDP on the observation space. And the last thing, which is kind of a technical point, is that I'm going to assume that every latent state is reachable, which means that for every latent state S, there exists a policy pi who can hit that state with good probability. And this eta will appear in our bounds. Okay, so let me just tell you an algorithm. I kind of want to go a little bit quick through this part because I think the other part is also pretty cool. I'm going to do like something very, very simple. I'm going to tell you like a sketch, which is like kind of obvious, and then we'll have to dig into some details. So you're going to just start with an empty policy. And for each time step, you're going to use the policy that you have to collect data. So you're going to roll in with this policy to time step H, the one you're currently working at, and take the H action uniformly at random. Then you're going to use this data that you have to learn some decoder for the time step that you're working on. So you're going to, the idea is that row H has good coverage over the state space at time H. You take a random action, you now have pretty good coverage over the state space at time H plus 1. You're hitting all the states that you could possibly hit. And now you're going to learn a decoder for the states at time H plus 1 somehow. And then you're going to, using the decoder, learn policies to hit all the latent states that you just discovered. And then your exploratory policy is going to be this like uniform policy cover over the policies you just discovered. And then that's it. So you just rinse and repeat this kind of thing. And so yeah, so the idea is that row H composed with uniform random action should give you good coverage at time H plus 1. And then, and this is sort of the picture, row H hits all the states at XH. You take a random action, you have pretty good coverage at time H plus 1. But you're going to pay a factor of the number of actions in terms of your coverage probability. And so what you'd like to do is this new exploratory policy should sort of like zoom straight to XH plus 1 and avoid this factor of H. So there's kind of like a boosting kind of thing that you're trying to do. You're trying to boost the coverage probability as you advance. And that's why we call this a forward algorithm. It like advances forward in time, where you first learn at time 1, then you learn at time 2, then you learn at time 3, and so it goes. And this forward approach is how you unlock the exploration and representation learning chicken and egg problem. Okay, but we have to answer a bunch of questions because I didn't tell you how to learn a decoder. I didn't tell you how to compute these policies. So we have to answer those things. Okay, so learning the decoder. Okay, I guess what you would love to do, which you cannot do, is just train a classifier. So there's these latent states. You have these observations. If I showed you the latent states, you would just say train a classifier to predict the latent state from the observation, and that would be a decoder, and it would be pretty good, and it would work. Of course, you don't observe the latent state, so you cannot do that. So this is like where the whole problem arises. So this kind of problem has been studied before, and when we started thinking about this, we looked at some stuff that people had done in the past. And this paper, this is this like curiosity-driven exploration paper that probably many of you know. What they do is they predict the previous action from the current and the previous state. Okay, and that's like kind of interesting. And we did a paper with like Simon Du and Nan Zhang and Alec and Miro, where we do this in this forward approach, and we predict the previous action and the previous decoded state from our observation. And so this paper, we were actually able to analyze this method, but it had some failure modes. And actually in the new project, we were able to come up with some very simple examples where these things kind of fail. So if you work through this example and you think about predicting the previous action from the current and previous state, you'll actually collapse these states together, even though these two states are actually should actually not be collapsed, in the sense that like there exist policies that hit them differently in different ways. So you can come up with, anyway, the point is you can come up with some situations where these kind of approaches fail. So we have to think of something slightly different. There's another thing you might do, which is just do unsupervised learning. And this kind of auto-encoding approach is very popular empirically. These are a lot of the ways these like count-based exploration methods work. It's also pretty easy to see that these things will definitely not work. So if you train an autoencoder, for example, if your state is a binary vector where one bit is the state and the rest is noise, there's nothing in your autoencoder that suggests you would remember the state bit instead of a noise bit. And in fact, if the state is has low entropy relative to the noise, then you're actually going to be encouraged to memorize the noise. It will minimize the reconstruction loss. So these autoencoding approaches may not work. There is this paper by a bunch of people at UCLA about doing, if you can formalize a guarantee that an unsupervised learning algorithm might get you, you can actually prove something. So that's kind of cool. It's just, you have to assume some structure of your problem for which the unsupervised learning will succeed, and then you can prove something. So that's pretty cool. But anyway, these things kind of work or require more, kind of don't work or require more assumptions. So let me tell you about what does work. So what we do is contrastive learning. You might have seen this in other contexts, but I've not really seen it too much in reinforcement learning. So we're going to collect a data set in a kind of strange way. So I'm going to roll in with some policy to visit some observation, take a random action, and visit the next observation. So that's x1, a1, x1 prime. I'm going to do this twice. So when I roll in again, I'm going to hit a new observation, x2, take a new action, a2, and then see x2 prime. And now I'm going to create a fake transition where I'm going to sort of assume that this is a fake transition that I'm going to use for my data set. I'm going to create a triple x1, a1, x2 prime. This is not a real transition that occurred in my environment, as far as I know, right? And now what I'm going to do is I'm going to train a classifier to determine if the transition was real or fake. So I can splice this data together myself and determine what's real and what's not, and I can train a classifier to distinguish these things. And so I have the label for this because I made this data set. Okay, and so that's what I'm going to do. And I'm going to train the classifier to have a special structure where it is actually going to map the second observation to a discrete value. And that discrete value is going to be the latent state that I learn. So this is a bit strange. So what I'm going to do is I'm going to take my predictor is going to map x, a, x prime. It's going to map x prime first through this phi function, which will be the discrete bottleneck. And then it's going to try to predict whether the triple is real or fake. And then this phi is going to be the thing I'm optimizing. That's going to be my latent representation. Let me go like 2 more slides and I'll take some questions. Okay, so that's a discrete bottleneck. Okay, so I think it's nice to understand a little bit why this works. So if you look at this regression problem that we're solving, the Bayes classifier has this very nice structure where it actually does not depend on the emission distribution. So it only depends on the latent state of the x prime observation. And if you massage this thing, you can see that if 2 guys get mapped together, then they'll have the same kind of ratio. And this actually will mean that the probability of hitting one of those states, hitting those 2 states is independent of the policy, or the ratio of visiting x1 prime and x2 prime does not depend on the policy pi, and therefore the policy that maximizes the probability of hitting x1 prime also maximizes the probability of hitting x2 prime. So this is this concept that we call the kinematic state abstraction. It's things that have the same kind of forward and backward dynamics. And here, this is basically these 2 things, x1 prime and x2 prime, will get grouped together because they have the same backward dynamics. Okay, and then the way you find the exploratory policy, there's many things you can do. You can just basically do like a dynamic programming approach where you like learn to optimize for this. You learn to hit one of these outputs of your bottleneck at the last time, and you learn a policy that only applies 1 step. Then you solve a contextual bandit problem over here, and then you keep doing this. So this is like a very standard kind of dynamic programming strategy over here. And let me tell you what we prove. So we're going to assume that the function class that we have, so we're solving this regression problem, and we have to use a class of bottlenecks. So we're going to assume we have a class of decoders that contains the optimal one, which means that it is possible using our function class to discover the latent state space. And we're going to assume this reachability thing that I told you before. And what we can show is that this algorithm can learn to visit every state. So it can cover the whole state space. And for any reward function, it can find an epsilon optimal policy using a number of samples, using a number of trajectories that scales polynomially in the latent state space, the action space, the horizon, this reachability parameter, the accuracy parameter. And this, you should think of it as like the complexity of the function class. So I'm using this set of neural networks. I'm paying for like the VC dimension of the neural network class, basically. But the fact, like we just analyzed this with the cardinality, but this is just like a standard supervised learning analysis. And so whatever you can analyze using supervised learning techniques, you can put that complexity measure here. And I guess what I want to say is because it's just a standard supervised learning analysis, nonlinear, this decoder class could really be nonlinear functions. Anything that admits generalization arguments is fine. And Homer, the algorithm, it runs in polynomial time. All we have to do is solve a bunch of supervised learning problems. So as long as these problems can be solved, then that's great. Okay, I guess there were some hands raised. How do I see whose hand is raised? They all went down.
You can just unmute.
Okay, if there are any questions, now is a pretty reasonable time to stop.
Mm-hmm. Yeah, so maybe I have there's a question. Okay.
Yeah, Dongru, you want to ask your question?
Mm-hmm. Yeah.
Do I have to unmute him?
Yeah, I just unmute him. Yeah.
Yes. So maybe I have a question. So it seems that you want to learn the decoder from the supervised learning approach, right?
Yes.
Yeah, and does that mean that if I recall it correctly, so it does not related to any specific learning method. Say you simply use the Zhang mean of this to get the best classifier among these finite samples, right?
Yeah, so we have to do a generalization argument, but we collect some data. So we collect some trajectories, and we just do empirical risk minimization over the data that we have.
Oh, okay.
And we need to argue somehow that the bottleneck that we learn is good enough, and that requires a statistical analysis.
Oh, so the mean should be consist of the two functions. The first one is f, and second
Yeah.
one is okay.
It consists of both functions, but we're just going to throw the f away. We only care about the phi.
Okay.
Okay, and we but there it's a good question, because this phi will not be the true decoder. It will be close in some sense that we have to quantify, because there's going to be statistical errors in this optimization problem, right? We're going to optimize from samples, something that we wanted to optimize in the population, and so we're going to have to do something here. There's something like non-trivial in the analysis there.
Okay, got it. Thanks.
Yeah, so I have a related question still about that empirical risk minimization problem.
Yeah.
Yeah, so it's is this optimization a non-convex optimization problem, or is a biconvex optimization problem?
Yeah. It's a good question. So this is a non-convex problem, and it's actually kind of nasty, because you have discrete output here, right? So it's actually not even differentiable, because you have you have to differentiate. F has some parameters, and phi has some parameters, but the output of phi is discrete, right? So there is something there's something that needs to be empirically verified. So the way I think about these problems is like, I don't want to deal with optimization issues as far as doing this like statistical analysis. So I like to abstract away computational primitives. So like the way we analyze Homer, we say, we assume that you can solve problems over data sets. We assume you can solve supervised learning problems over data sets.
Okay, so during the proof, I assume you are using some plugin argument, but do you need to assume that the f hat and the phi hat here is the global minimizer, or it could be just the first order?
Yeah, that's a good point. We assume it's the global minimizer. So that's a bit, we assume you can actually compute the argument.
Okay.
Right, and you're right. That's not obvious. I mean, that's difficult, right?
Okay. Yeah. Okay.
Thank you. I think there's one more question. Yeah.
Hi, I need to ask, when you're learning this decoder and the data you're collecting, is it learned on the fly, or you kind of collect the data at once and then learn it like in a single path?
Yeah, that's a good question. So we do this in batches, one for each time step in the problem. So we have capital H steps in the episode, and we first learn a decoder for time step 1, then we collect a whole bunch of experience, then we learn a decoder for time step 2, then we collect a whole bunch of experience, and we repeat. So it's not an online algorithm.
Is it the same decoder refined, or is it like different decoder learned for a different time step?
It's a different decoder learned for each time step, but that's kind of like, that's like to make our lives easier for the theory, because we're just assuming that states at time step 2 cannot be reached at time step 3. And therefore the decoder you have at time step 2 is not useful at time step 3 at all. But you're right that that's like empirically not the case. And so we should try to use all the data we should be refining the decoder. That we haven't thought about it, but I think that's the way you want to do this in practice.
Okay, thank you.
Okay, let me keep going. So anyway, so that's the main guarantee. And let's just return to this exploration problem. Remember that you have these high dimensional observations, you have this hard dynamics, anti-shaped reward, and this long horizon. So let me show you what Homer does. I mean, this is not going to be surprising. Okay, so PPO I showed you before, it basically does not even make it to state time step 5 or 6. We also ran some algorithms that empirically are good for exploration, like this random network distillation approach. So this is, I think, random network distillation as an exploration bonus on top of PPO as the policy optimization method. And this one is pretty decent. So it like gets to time step 28, but R&D has some kind of variance issue where if you know how it works, if it maps two observations to the same latent, the random neural network maps two observations to the same vector, then you'll not have a prediction bonus later on, and then you'll fail to explore. So when you ask it to do this like 100 times, it will fail at some stage. So we like somehow R&D has a little bit of high variance here. It's kind of unstable, and Homer is just like completely stable. It just like nails this problem, and it's able to explore the explore all time steps. We're actually also able to recover the latent dynamics for the most part, but we didn't prove anything about it, so I'm not showing you here. So that's like the block MDP and this Homer algorithm, and I like this model because it forces us to reason about nonlinear function approximation, which is actually very difficult to reason about in reinforcement learning, and a lot of people go through lengths to avoid reasoning about it because it's kind of hard. It can model rich observation problems like visual navigation, and Homer shows that it's statistically and algorithmically tractable, and it's actually gaining quite a bit of interest from the community. So like, we've worked on this problem, but there's this group at UCLA that did this, and this group at MIT that's also been thinking about these problems as well. So that's kind of cool. But like what Sean was mentioning, there's some downsides to having a discrete finite latent state space, which is your optimization problem is very difficult. And we have experienced some headaches with this in practice. And there's this other thing that's kind of maybe a technical point, which is like, there's no reason to demand decodability of the latent state as long as you can plan and approximate the optimal value and optimal policy. So I like didn't really see why we needed decodability in this problem, and I was thinking maybe there's a way to retract this. But I think point one is really a headache, and I think something that might be a problem when we try to develop practical algorithms. So anyway, we were thinking about this, and that sort of brings me to the next part of the talk. If there's like a quick question, maybe now is a good time. Otherwise, I think the timing is pretty good. Cool. So this is about this new paper. This will be a oral at NeurIPS this year. So this is about low rank MDPs and this algorithm called Flambe, and this is joint with Alec, Sham, and Wen. So this model, I really like this model. This is this low rank or linear MDP. It has many names, but I like to call it low rank, where the transition operator, so this T is it associates a distribution over the states with, or the observations with each observation and action. And this transition operator, we're just going to, you can write it as a matrix, and we're just going to say the matrix is low rank. Okay, so this T operator can be written as the inner product between some phi feature and some mu feature, where phi takes xa as input and mu takes x prime as input. And what I'm going to assume is that the embedding dimension, which is this side, the dimensionality of the feature maps is relatively small. It's d, and it's going to be much, much smaller than the size of the observation space. So that's like the assumption. The assumption is your T operator has this low rank factorization. And what I'm not going to assume that you know this feature map or this feature map. I'm going to assume these things are latent. Okay, and that's the representation we're going to try to find. Okay, so these are the things we're going to try to learn in the representation learning setting. Just as a tangent, okay, block MDPs happen to be low rank. This is like a pretty easy thing to see. So in the block MDP, because of decodability, each observation can appear from at most one latent state. So I'm going to associate each latent state with one factor in my matrix, and that makes this matrix has to be block diagonal. So all the blue area has to be 0, and the orange area can be whatever you want. It also has to be the case that the features over here are on the simplex. So block MDPs are low rank. So if we can solve the low rank model, we automatically solve block MDP, which is great. But we actually solve much, much more, because it's very easy to see that there are low rank MDPs that do not admit any non-trivial block factorization. So you have n observations, and to write it as a block MDP, you need n latent states, which is just completely trivial. So when we solve the low rank MDP, we're going to do much, much more than block MDP as far as modeling is concerned. I want to return back to this decodability point. So you can also write, there's another special case of the low rank MDP where both of these matrices are row stochastic. So the features live on the simplex, and the rows of this matrix live on the simplex. And this model is pretty interesting and pretty nice. It's a special case of the low rank MDP, where you can view it like a latent variable model, where when I want to transition, I'm first going to sample a coordinate from this distribution. So I'm going to call that a latent variable z. And that's going to give me a coordinate. So then I'm going to sample my next observation from the row of the mu matrix induced by that coordinate. So each row here is a distribution. and I'm going to sample from the row indexed by my latent variable. So this can be seen as a latent variable model, just like the block MDP can be seen as a latent variable model. Except here, the latent variables are not decodable because, if given that you see X prime, that should be an X prime, you don't know which Z produced it because I'm not telling you anything about the support. So that's cool. Still not an HMM because you don't need to see the whole history to do this posterior decoding kind of thing. And this model has been studied before in some prior works. Okay, but that's like all kind of for fun and games. Maybe we should ask, why should we care about this problem? Well, the first point is that this problem is actually tractable. So if you know the feature map, then it's possible to get something like square root t regrets that scales polynomially in the dimension when the feature map is known. And this is this paper by Chijin, Xiaoran Yang, Xiaoran Wang, and Mike Jordan. There's another paper by Lin and Mengdi that does something kind of similar. That's cool. So at least the latent model is tractable. It's actually tractable even in the representation learning setting. So this is, it's statistically tractable in the representation learning setting. So this is this paper we did with Nan Zhang and Rob Shapiri, where we come up with this combinatorial parameter called the Bellman rank. And you can prove that the low rank MDP has Bellman rank at most the dimension of the latent feature map. And if you have a class phi of candidate embeddings, and the true one lives in this class, then this algorithm we developed in this paper actually gets a sample complexity that sort of scales the way you want it to. So it scales polynomially with the dimension and logarithmically with the size of this class of candidate embeddings. So that's cool. So this problem is actually statistically tractable. However, this algorithm, we don't know how to really implement it. It's kind of like an enumeration algorithm where we like try all of these embeddings, and we don't have a nice way to implement this algorithm. So the goal in this project is to basically achieve a very similar result, but in a computationally efficient manner. By the way, I mean, that was also the goal in the previous project. So Olive also addresses the block MDP setting, but it's not computationally efficient. So homework can be seen as, how do you take this information theoretic algorithm and make it computationally tractable? And that's what we're going to do here for this richer class of models. Okay, so this is what we proved. So it's going to be a model-based algorithm. And so what I'm going to assume is that you have a function class phi, like in the Olive approach. You also have this other function class upsilon, and they contain the true dynamics. So the true left factor is in phi, and the true right factor is in upsilon. And we're going to assume as our computational abstraction that you can optimize and sample from these functions. So I probably won't tell you much about sampling, but you'll see how I want to optimize. Okay, and then what we prove is that this algorithm Flambe, it can learn a low rank, it's a model-based algorithm. So it's just going to output a low rank MDP model. And that's going to have a phi hat and a mu hat. And what I can prove is that for any policy pi and any time step h, if you roll in with policy pi to time step h, and then you measure the one-step error in your model, it will be small for any policy pi and any time step h. Okay, so this is like a universal approximation of the system, no matter in any place that is reachable. And we can do this with the sample complexity that scales polynomially in the dimension, the number of actions, the horizon, the accuracy parameter, and the statistical complexity of the function classes that we're working with. Again, this is just like standard generalization, almost a standard generalization argument. So you can use nonlinear functions here, no problem. I just want to point out that we've removed this reachability requirement from Homer. So that's like a nice technical point. And yeah, the algorithm runs in polynomial time, assuming you can optimize and sample from these functions. Okay, so I should also tell you something more precise about representation learning. So we actually do discover a good representation in a formal sense. So we learn a model, an MDP model, low rank MDP model M hat, which has these features phi hat 1 to h. And this low rank MDP has this really nice property that the optimal, for any reward, the optimal policy and Q function for this model are linear in these features. Now, the system identification guarantee actually implies that in the true world, a near optimal policy is linear in these features. So in this sense, what Flambe is able to do is it discovers a representation hat phi, which allows you to approximate all the quantities you care about in the real world. Any value function, any Q function, any policy will be linear in your features. So that's kind of cool. It's like a very formal way to say something about representation learning. This also gives you a form of reward-free learning, because we did this whole thing without any reward. I haven't told you about a reward function at all. And you get a model. And now if you want to, if I give you a reward function, you just optimize for it in the model, and that will be good enough. And you don't have to collect any more data to do that. And we're also able to do something where you don't have to use sampling. So you just plan in the real world and replace sampling in the algorithm. But we currently don't know how to do this without the reachability part. So the way we do this is using reachability. There's a plus here where we don't have to sample, but there's a minus where we need reachability. Okay, let me tell you about the algorithm. Again, I'm going to tell you something. It's going to look very simple. Okay, so you start with a random policy. And then you're just going to repeat this thing over and over again. You are going to collect some data using the previous policy. So you have this row j minus 1. You're going to roll in with it for h time steps. And then you're going to take the current action uniformly. And you're going to collect a transition. And you do this for each h. Okay, so now you have a bunch of new data. And what you're going to try to do is you're going to just, for each h, learn the dynamics for that time step using all the data that you have. Then, okay, this is very vague. You're going to compute an exploratory policy, a new one, row j. Okay, and that's it. That's what I want to tell you about the algorithm. I basically didn't tell you anything. Again, the intuition is very similar to what's going on in Homer. What you want is that row j will induce good coverage over the state space at time step h. So now, row j minus 1 covers the state space at time h. You take a random action, you have pretty good coverage at time h plus 1. And ideally, now that you've learned this dynamics, when you plan, you can plan to just zoom straight to time step h plus 1, and you will advance forward by 1 step. And you will not pay this factor of number of actions to do this. So that's the idea. But this one is a little bit harder to think about than in Homer, because, okay, we have to figure out how the heck do we learn the dynamics? And then we have to figure out how do we, I mean, I said you want good coverage, but I don't even know how to measure it because the state space is arbitrarily large and there's no like latent state that you can use to measure coverage. So we have to think of something else. And computing the exploratory policy will also be kind of complicated. So we have to answer these 3 questions. And I think, okay, this is like not exactly how the proof goes, but I think this conveys like all the basic intuition. So there's 3 questions. The first question is, how do you learn the dynamics? And the answer is you just do maximum likelihood estimation, which I guess is probably the most obvious thing you could try to do. It turns out it works, although this was like very surprising to me and something that I've not seen actually used in the function approximation setting for reinforcement learning. How do you measure the coverage? Well, we're going to use the true feature covariance at the previous time. So let me show you a picture and it will make sense. And then how do you compute the exploratory policy? We're going to use the learned features at 1 time step even further back. Okay, so we're going to do maximum likelihood estimation to learn the dynamics from h to h plus 1. We're going to determine that we did a good job by measuring the coverage in terms of the true feature at time step h minus 1. But unfortunately, we actually don't have this in our hand. So we can't optimize against this function. We can't optimize the covariance at time step h minus 1. So instead, we're going to optimize the learned feature covariance at time step h minus 2. And this is going to give us good coverage. So the picture is, you have to think about 4 time steps. The first question answer is all the action is taking place here. And I'm just going to do density modeling. I'm going to do maximum likelihood estimation. The second question, all the action is taking place over here. And here I'm going to try to measure my exploratory policy. I'm going to measure the true feature transpose of this exploratory policy at this time step. And what I would love is for this thing to be have very large eigenvalues. Of course, I do not know this thing because I do not know the true features. So I cannot actually plan to make the eigenvalues big. Instead, I'm going to plan to make the eigenvalues big of the previous time step. So the last question, all the action is happening over here. And that's what I'm going to do. So this is my learned feature phi hat. And I want to make sure that my exploratory policy has big eigenvalues in phi hat space. And this will sort of imply it has reasonably big eigenvalues in phi space at the next time, which will imply that we have reasonably good coverage at the state space at time h, which will give us good density modeling accuracy. So that's the kind of idea. Let me walk you through some of the steps. Actually, maybe now is a good time for questions. I think the timing is pretty perfect. So if there's any questions, we can maybe take 1 minute. Yeah, go ahead. Someone has raised their hand, but they're not talking.
Yeah, I think you can unmute yourself to talk. Hello?
Oh, ask to unmute. Okay.
Yeah, ask to unmute. Yeah, so maybe, so I have a question. So when you say density estimations or density estimators, what kind of density estimator you are using?
Yeah, I'll show you on the next slide.
Okay.
I will use my function classes to do maximum likelihood estimation. It's like, you should think about it like parametric maximum likelihood estimation.
Okay, and what kind of distribution do you assume? Is a Gaussian distribution?
No. Yeah, it's a bit strange. I'm thinking about this like, think about it like the statistical learning. Maybe I'll go to the next slide.
Okay, sure.
Yeah, so now we're going to talk about this one.
Okay.
Okay, so I'm going to collect some data, xh, ah, xh plus 1, from some data distribution. This doesn't really matter too much. And I'm just going to solve this log likelihood problem. So I have these function classes, capital phi and capital upsilon. I'm just going to say, search over my function class for a pair, phi and mu, that maximize the log probability of the data. So this is, if you believe the dynamics were Gaussian, this would be Gaussian density modeling. But I'm thinking about this very much in the like abstract setting, where it's like, you just gave me function classes, they happen to be densities, they happen to output probabilities, and I'm going to maximize the log probability. So this is the precise optimization problem that I'm going to solve. And you're going to get some, phi hat and mu hat out. And what was quite remarkable to me, I did not, this is not my theorem. This is Tong Zhang's theorem. Actually, it's more classical, but I think he has a very nice version. So if you assume that the true feature maps live in capital phi and capital mu, that's realizability, then you will guarantee that the total variation distance between what you learned and the truth is bounded by something like 1/n, where n is the number of samples you have. And I guess I want to point out that this is on the data distribution with which you're collecting the data. So this is like, it's like almost a standard generalization argument, except this loss function is unbounded. And the expected value of this loss, or the risk, is the KL divergence, which is also unbounded. So instead, you cannot do generalization. You cannot do uniform convergence in KL, but you can show that the total variation, which is bounded, will be small. So that's pretty cool. So this is like this, I think there's this line of work on like fast rates with unbounded losses. So this is kind of like that.
I see.
Okay, so let me call this the error. A technical point which we have to use is we actually prove a martingale version. So rho I depends on all the data you've seen before. And so I want to make sure that the error is good. I can accumulate all of these things to get more data. So I have to prove martingale version, but that's not too bad. So this is basically the guarantee that we have. And let's move to the next part. So the next part is the potential function, which is the time step h-1 to time step h. So here, I guess this is sort of like where I think all the magic is happening. And I'm using this key property of the low rank MDP. So for any function f and any policy pi, the expected value of f at time step h when I roll in with policy pi can be written as an inner product, a d-dimensional inner product, where the first term is the expected feature of policy pi at the previous time, and the second term is something that depends on f, right? So phi times mu is the transition operator, and so this is like there's a trend. I've taken this expectation. There's a hidden transition operator there, and I'm just writing it out explicitly, and it looks like that. And this is amazing because see, this term does not depend on the policy pi at all, and this term is very nice. It's just a d-dimensional function. Okay, so that's like where the potential function is going to arise. So what I'm going to do is I'm going to define this sigma, this covariance operator, which is the feature transpose for my exploratory policies. And just rewriting the error guarantee from the previous slide, you will get something that looks like this. This is like basically just rewriting. Maybe you have to use Jensen's inequality one time. Okay, so you use this property. So this is the over here is like the total variation error. And this is the dynamics at the previous time. And so what you can see is that this is just a d-dimensional vector norm that is hiding the total variation error there. And that thing will be pretty small. So that thing will be like 1/n plus some regularization term, which is just, I'm going to set lambda to be very, very small. So that'll be great. So let's call this d-dimensional vector, this norm, the error for the covariance. And now I'm going to use this property again, and I'm going to do change of measure. So I'm going to roll in with some new policy. I'm going to look at the error. I'm going to rewrite it using this key property. And then I'm just going to do Cauchy-Schwarz. So I'm going to multiply and divide by, I'm going to multiply by the sigma, and I'm going to multiply by the sigma inverse. And I'm going to do Cauchy-Schwarz, and I'm going to get something. And the one term is just going to be that error function, which I know to be small. And the other term is going to be the norm of my feature at the previous time when measured against this covariance matrix. And this is like the distribution shift coefficient. So the point is, if sigma is very big, then this norm is also very small. And that's where the potential function is. What you would love for your exploratory policies is to have a very, very big sigma. And if that's the case, then no one can have any total variation error, right? So this is the total variation error of policy pi, and it's just small if your sigma is big. So that's the idea. The last part is that you want your sigma to be big, so you want to find policies that maximize the inner product against the sigma, but you can't because you don't know phi. Okay, so this is sort of the hard part. You don't know this potential function. So what you're going to do, hey, what's up?
Can you go back to the previous slides? Previous one. Can you elaborate more about how to get the second equation, the error transfer?
Yeah, I think you should just write it out. It's very straightforward. So, okay, do you understand this one?
Yeah.
Yeah, so it's basically the same thing. So I think you start here, you expand the square, then you get like transition times mu and another transition times mu on the other side when you expand the square.
Okay.
And then you do Jensen's inequality to push the square inside or the square outside or something like that. It's very straightforward.
So how about the right-hand side? How to get that? The right-hand side.
Oh yeah, you'll see it because there's a lambda sitting here, and this feature is bounded in norm, so that'll be lambda times d. And then the other one is you'll actually exactly get this expression.
Okay.
That'll be the other one. Yeah.
Okay.
Yeah.
Yeah, that's clear. Thank you.
Yeah, so that I think is pretty cool. That's something like, I mean, we use this fact, like, this is now my new favorite fact, and we use this fact all the time. It's just really incredible. Okay, so we want to make sure that for all policy, we want to make sure that the sigma inverse, no policy can make this quadratic form very big, because if that's the case, then we'll be done by that error transfer argument. And if I maximize this function and I include the new policy I find into my exploratory policy cover, then this cannot happen very large, happen many times. This is this elliptical potential function argument that's used all over the place in linear bandits and stuff. Okay, but the issue is that we don't know this feature map phi, so we cannot actually plan to maximize this. And so what we're going to do is we're going to plan to maximize the phi hat at the one time step even further back, phi hat h minus 2. So we keep solving this maximization problem. Also, this is in our model, okay? And we're going to make sure that our exploratory policy ensures that no other policy can have a large quadratic form against rho's learned feature covariance inverse. And we use, again, this elliptical potential argument here. And the point is that if you have good total variation error up to time step h minus 1, then by virtue of the fact that no one can have good inner product against your inverse covariance, you actually approximately optimize this objective over here. So that when you sort of write things again in terms of the dynamics, you use the total variation guarantee to translate to the model, and now you get to use the potential function in your learned features. So that's the idea of how to get that one. And that's like kind of how the proof goes, but that's not exactly how the proof goes, because the last step here, you need to assume you have good total variation error, and we might not. And so we actually use a slightly different argument where there's like a simulation lemma with some escaping function. And we somehow say that if your rho does not maximize coverage, then it must escape, which enables you to learn at some previous time. So this is a bit technical. I think that the 3 steps before are basically how the proof goes, and that's like kind of the main ideas. But if you read the paper, you will not really see that. It will look like something different. So that's, this is what's actually going on. There's this escaping argument. Okay, so I just want to take a step back because the time's about up. Here's like sort of my view of the landscape. I realize I'm definitely missing some stuff here, but so the block MDP. So for all these problems, you can think about like the known representation setting and the unknown representation setting. And so the known representation version of block MDP is just tabular MDPs, which like we've known how to solve since Kearns and Singh's seminal paper in 2002. And we have like the optimal rates these days and like instance dependent bounds and all sorts of, like there's tons of papers on this topic. The low rank MDP, the known representation setting is what people are calling the linear MDP, which is this paper by Jijin and co-authors and the paper by Lin Yang and Mengdi Wang. And a bunch of other people have started studying this in the last 2 years. Okay, this one is not really like, okay, this is sort of not exactly on brand, but there's a much bigger class of problems that we know to be tractable, which are these ones that we've characterized using these notions of Bellman and witness ring. But these are only statistically tractable, and we don't have efficient algorithms over here. Okay, so now you can ask, in all of these problems where we have efficient algorithms, what can we do about representation learning? And so for the block MDP, we're able to do something. So this is like all this stuff I sort of mentioned before, including Homer. And for the low rank MDP, Flambe is able to do, the unknown representation setting. This is sort of like the one way that I think about the landscape of this kind of stuff. But there's still all this stuff out here that we would love to get efficient algorithms for, and we don't know how to do it. So yeah, so this is the last slide. So this is sort of the way I conceptually think about this line of work. I want to solve like, complex reinforcement learning problems where you have to explore and you have to use nonlinear function approximation. I don't really know how to do this in general, but I think a way to think about this is you take a model that you know to be tractable and you attach the complex observation process to it. And so that's what I'm saying here when I say decouple the dynamics from the observations. And the block MDP and the low rank MDP are like very perfect examples of this. And this approach I feel is kind of nice because it forces you to use nonlinear function approximation because you're going to make very weak assumptions. You're going to make almost no assumptions on what the observation process looks like. But because the dynamics are relatively nice, it will remain tractable, I hope. And we've been doing this kind of, or like MSR New York folks have been doing this kind of a lot. So like there's a couple people who have a paper on factored MDP, which we know to be a tractable problem without rich observations, but they've attached rich observations. We have a paper on doing this for linear quadratic control, where you attach rich observations. And so, this is like, you can do this for lots of problems. And I guess I don't want like us to write a million papers on this, but I do want us to discover good algorithmic principles. And so the way I'm thinking about it is like, we work on these problems, and as we do this, we will learn about what it takes to make a good algorithm that does exploration and nonlinear function approximation. So that's like the conceptual way I think about it. We've had some, at least in theory, some success in these block and low rank MDPs. And okay, yeah, so you might ask, does it actually work? I don't know. We are trying. I have a postdoc who's like very good at empirical stuff, and we're trying to get these things running. And so hopefully in 1 year, we'll have some progress on that. Okay, so yeah, here's some links to the papers. You can find them online or on my website or whatever. And let me just wrap up by thanking all my co-authors. This is Alec, Michael, Sham, John, Dipendra, and Wen. And yeah, I'm happy to chat more, take any questions. But yeah, that's the talk.
Yeah, thank you for the great talk. Yeah, let's take questions. Take more questions.
Yeah, the questions so far have been quite good.
Hi, maybe I have a questions about the presentation. So can you turn previous slides, which yeah, previous according to the definition of the definition of the factorized MDP still previous.
Oh, the factorized, the low rank MDP.
Yeah.
Oh, okay, yeah, I'll go back. I didn't really give you a precise definition, but
yeah, just here, the total variation here.
Oh, this one.
Yeah, here. Here, I'm just a little bit confused. So, here you want to find this representation for the phi and the mu here, right?
Mhm.
So is that true that you can guarantee like the argmax of the phi and the mu, these two can be combined and to represent an MDP? Since you need do you need additional constraints? Is you want not only find argmax phi and mu to maximize the MLE you presented later, but still you need these two can be combined with a probability transition, or do you not need this kind of constraint?
Yeah, so okay, that's a good question. So I think the way that I would think about this is like, suppose we let's think about this simplex features case. So what I'm going to do is I'm going to the way that this function class should incorporate some domain knowledge. Okay, that's like every time I see this kind of expression, I'm thinking these function classes incorporate some domain knowledge or some inductive bias that I have about my problem. And so what I'm going to do is I'm going to make it so that the output of any phi is on the simplex, and mu of dot is a distribution. So then this is always an MDP.
Okay.
Right. So that's like that's this one. So here I'm assuming this is rho stochastic and this is rho stochastic, and that's like a particular way to parameterize your problem.
So the simplex assumption is necessary or not?
It's not necessary, but somehow you're right that you have to, you do need to sort of, okay, MLE does not really work if your outputs are not distributions, right? So so you need to sort of have it be the case that these are any pair of phi mu will be a transition operator, and that's like something you have to bake into your function class somehow. I'm not like explaining or assuming that. No, I'm assuming that the domain practitioner is able to do that.
Okay, got it.
Right.
Got it.
And like the simplest way I think is to do the simplex features, but maybe there are other ways. I'm not constraining you.
Yeah. Okay.
Yeah.
Okay. Thanks.
Yeah. I think Sandeep has a question.
So I need to ask a question about the first part of the talk where you compared with the PPO and you raised a problem about it getting stuck in state space while exploration. So what was the motivation behind PPO only? Like, can other algorithms like the value based or even deep Q learning based, which have random exploration in the beginning? So can those algorithms solve this problem?
Yeah, that's a good question. Basically, no. So we tried DQN, PPO, A2C. We attached R&D to a bunch of these. We actually tried a bunch of stuff. I'm just showing you like a representative example. So I think, I mean, I think this is kind of like a good exercise. When you have an algorithm, you should actually try to break it, right? So we took all these algorithms that people are using and we're like, okay, how can we break them? And that's how we came up with this. I'm
asking this because like in most of the real robotic examples, people always use kind of PPO based algorithms for real robots. So if you're showing that PPO breaks, then there is something serious which we don't understand now.
Yeah, I think, okay, so what's serious that we don't understand is how to explore. But I think in a lot of robotics problems, you don't, well, a lot of the like easy, like Mujoko problems, you don't have to explore that much. Like the hard ones, I think you do, but here, like this problem is like very, very, okay, I didn't actually say this. If you took random actions here, you would take 10 to the 100 episodes to hit the reward because there's 10 actions here and you have to do this 100 times. So really, like, you should not expect a random search method to get anywhere. Right? Like 10 to the 100 is like more particles than there are in the universe, right? So you should not expect anyone to get anywhere if you do random. And so the thing that we don't understand is the ability to explore. And I think a lot of the times that we see things succeed, this is my personal take, is like we don't, those problems are not hard as far as exploration is concerned.
I see. Yeah, that's a good point. Yeah.
And that's like R&D, I think, is actually pretty good. Like I would advocate for R&D in practice until we have something better.
Okay, thank you.
Yeah.
Hi, I have a question about the block MDP setting. So as you mentioned that when we have a known representation, we can just treat it as a tabular MDP, right? But if we don't have the representation, can we still just treat the observations as more specific states, and so that we have a very large state space and just use tabular MDP methods to solve it? And can we do?
Yeah, okay, you could, but it wouldn't go very well for you, because when you run a tabular MDP method, you're going to pay for the number of states, right?
Yeah,
and
I remember I remember one slide about the cost of the Homer algorithm. There's also state size, right? Although it's just the state size of the latent state, right?
It's the latent state space.
Yeah. So is there any comparison in theory about some setting or empirically about what we will lose and use if we just treat all the observations as states too?
Yeah. So I mean, in like the observation space in this model is infinite, and you will never see the same observation twice. So you could run a tabular method, but you would just not get off the ground because you would not be able to maintain statistics about all. I mean, you would never see the same state twice to learn about what the dynamics look like from that state. Your table precludes you from finding this dimension reduction out, this low dimensional place where you can collapse all your statistics. And so basically, if you were to run a tabular method directly, you would pay for, where's the theorem? It's coming. This cardinality of S would be number of observations, which is infinite. I mean, that's like the only way I know how to apply those things. Maybe there's a more clever analysis, but I highly doubt it because you're lacking the ability to generalize.
I see.
Right.
I see. But the latent space and size, could that also be infinite in some case, or we can?
Yeah. So it could be, and I mean, this is sort of what the low rank MDP is doing. And the low rank MDP is a more general model, but I think you should think about this like, what are the class of problems that we're able to solve? And the block MDP is a richer class of problems in the tabular that we are able to solve. And there are problems beyond that we're not able to solve. That's totally true. But this is pushing out the frontier of what we can do, provably.
I see.
Right.
Thank you.
And then the low rank MDP is even further. So maybe this. So this slide. So in the low rank MDP, all you have to assume is that this embedding dimension is D. In the block MDP, you basically additionally assume that this matrix is block diagonal. But this operator is, I mean, we're not going to assume anything about the size of this operator. This is going to be arbitrarily large by arbitrarily large. And what I'm saying is, what this proposition is saying is that if you were to write a low rank MDP as a block MDP, the number of blocks might have to be as big as the number of observations. So then if you were to apply the Homer theorem in that setting, you would lose because the number of observations, you'd still pay Pauli number of observations. Yes. But it could be the case that there exists a low dimensional embedding. It just does not obey this block diagonal structure over here. So it's not a block MDP, but it does allow, but it still would allow you to get a tractable algorithm. So this is like the point is the low rank MDP is a much richer class of models that is also tractable. So the second paper is pushing this boundary out even further of what we know to be tractable.
Okay, thank you.
Like certainly it is the case that there's going to be problems where the transition operator is completely unstructured. There's no low rank, there's no block, no nothing. And those, I guess I currently believe those are not tractable at all. Maybe there are some other structures that we can still solve, but not with these methods.
Yeah. So any other questions?
Oh, maybe I can make a plug. So MSR is hiring. So if you're interested, maybe shoot me an email. That's the best way to do this. And we're also looking for interns who, we're hiring in all sorts of areas, but like I mostly work on reinforcement learning. So shoot me an email if you are interested in intern or like postdoc or researcher positions. And we can try to see if something works out.
Yeah, thank you for the opportunity.
I have to do my job, right?
Yeah, that's great. Yeah, I think there must be students will follow up with you. Yeah, both regarding your work and maybe also the job.
Yeah, either one is fine.
Yeah. Yeah.
Yeah.
Okay.
Okay.
So